Thank you, organizers, for the opportunity, and I really thank you that you put the talks in a very appropriate way, because now I feel like everything is already said, and I don't need to spend so much time for the definition of the thing. This is a work. It's kind of a basic work. It's just me trying to learn a bit of how to do dynamics with the simple integrable systems. So I'm having quite a fun. It's based on a bit of work that we did, small work with Sona Najafi. She's a student in Georgetown University, and some ongoing work. And since I arrived here, I actually had a very productive discussion with Jacopo, but that's not the part that I'm going to talk about it. But it has been pretty useful. So, the outline of the talk is going to be, well, I'm going to talk a bit about quantum quench and revivals in conformal-free theories. I'm not going to talk about really conformal-free theory results and how the techniques, but just some historical and introduction about the things, because my background is CFD, and that's the reason I'm more comfortable to start with this kind of stuff. Then I'll talk about quasi-particle picture, and then I'll start to talk about XY chain. Then I'll open a parenthesis and I'll talk about something which is not dynamic, but it was a kind of a motivation for me to study what I'm going to talk later. This part I already gave a full talk last year, but today I'll just spend like maybe 10 minutes to just motivate and introduce some new things. Then an initial state effect on the Loschmidt echo, and initial state effect on the revivals of correlation functions. And finally, for just fun, I'll talk about also a bit about Shannon information. So, global quench, as far as I know, well, I don't know, I don't have a control on this animation. So, the global quench, the definition is just a prepared system in the initial state, C0, which is the ground state of, let's say, the Hamiltonian H0, and then just evolve it with another Hamiltonian, which is different from H0. So you kind of, you can think like you are pumping some energy at the time 0. Well, but basically, it's just you start with the initial state, which is not the eigenstates of your Hamiltonian H. Then it's just study the evolution of correlation functions, Loschmidt echo, entanglement entropy, and all these things. Now there are like thousands of works regarding this kind of questions. Well, in CFD, this is, as far as I know, it's started, well, I'm sure that it started first by the Calabrese-Cardi for the global quench, and then they actually calculated the correlation functions, entanglement entropy after the global quench. And as far as I know, I think they were the first that they introduced the word quantum quench. So it's kind of appropriate to talk about their work. And then for the local quenches, it was done for the CFTs by the Dubai and Stefan. This is not the part that I'm going to talk, but it's kind of interesting. Then there are many people that they have been doing the quantum quench for the discrete models, and I'll come back to some of them, at least those that I know about them. Right. So, based on the work of Cardi Calabrese, you can, after the global quench, in conformal-free theories, you expect that the operators, we call them scaling operators, they decay exponentially fast. But the two-point functions, they usually follow this kind of behavior. But when you look to the connected case, then you see that there is some sort of a light cone behavior that I will come back later. But this is mainly was the initial, work in this community of the quantum quench, as far as I know. And so the important point is that this, as I said, the connected correlation function, two-point function, is going to be 0 for some time, and then it's going to be finite. And this is actually true, not necessarily for conformal-free theories or critical system, but it's true also for integrable models that are not necessarily critical. And that's mainly because of the famous Lieb-Robinson bound. Another interesting thing that this is also a work of Cardi is that how one can actually study the Loschmidt echo in the conformal field theories. You know, the Loschmidt echo that I define here is even simpler than what the previous speaker talked about. It's just you start with the initial state, and after some time you just ask what's the probability of this guy to be the overlap of this guy with the initial state. And so this is something that usually I consider is interesting in the context that I'm going to talk, when you have a finite system, and then you quench the system, and then you want to see that what's the probability of this guy is going to come back to itself, and that's what I call revival. And is this based on this very interesting work by Cardi, you can show that in CFDs, these are some mathematics, you know, it's not important, but just the message is that you can see that in some particular conformal field theories, you will have some revivals that they are actually going to happen in the times that they are proportional with the length of the system. Well, this is normally any kind of revival for me in many-body systems is a bit strange, because you have a many-body system and you have this huge Hilbert space, and you don't expect these guys to come back to themselves. So that makes the work pretty interesting, that if you have some critical system, then there might be some funny revivals in the system. But at the same time, it's a bit suspicious, because, you know, it's something that conformal field theory, the field theory is something that usually you can use it when you are around your ground state and not far from ground state, and you don't have really excited states. So when you have a finite system, normally you excite a lot of excited states, and that makes it a bit questionable that you are able to even use field theory techniques. So that's the reason that, you know, I started to get interested that to see the limitations of the field theory techniques in calculating dynamical systems. Well, so this is the story that initiated all the things for me. Here, before going to more concrete model, let me tell you about a quasi-particle picture in this community that we work. I mean, based on this, the proposal by Calabrese and Cardi in 2006, this is a picture that I borrowed from the review by Essler and Fagotti, so that's the reason I put it here. So when you start with the initial state, this initial state, we usually say that it has an extra energy, and then extra energy means that, you know, when you expand it with respect to the eigenstates of the post-Hamiltonian, then you have a lot of excited states in your expansion. And then this initial states, then you can think like semi-classically that it's producing a lot of quasi-particles. And these quasi-particles are produced at every point, and then these quasi-particles, one goes to the right, and then the other goes to the left. And then if you have if you are lucky, and then you have one kind of quasi-particles, then these quasi-particles can actually tell you when you might have a correlation in your system. So this picture is like that. So if you think about the connected correlations, then the correlation of these two guys are going to be non-zero whenever this light cone in the reverse direction, they overlap with each other. So before, you don't expect any correlations, and then after that, you expect something like that. This is actually probably people that they were working with Lieb-Robinson bound and stuff. They were imagining that something like this might be true in some cases. any case. Well, but this is a very simple explanation. It actually explains the first formulas that I wrote for based on the Calabrese and Cardi explanation for the conformity theories. Well, so let's start a concrete example and study some of these things. So the concrete example is the XY quantum chain. It popped up a couple of times, so I will not go too much to the details. This is the definition, but usually we work with the fermionic version of this guy, which is this one, and I will mostly work the case that the n is equal 1, which is I'm going to take a periodic boundary conditions, but most of the things that I'm going to tell are more or less valid for also open boundary conditions. But in principle, I like to do things analytically, so it's not really easy to do things analytically for the open case. So everything will be either n equal 1, but n equal minus 1 also are manageable. So for later use, I prefer to write this guy, this Hamiltonian, in this form, and with this matrices. And of course, you can diagonalize it by going to the momentum space, and then you will have this Hamiltonian with this dispersion relation and with these group velocities. And I will use this group velocities pretty regularly. Okay, so this is the model, and everybody knows about it. Something that the phase, we know the phase diagram almost for 40 years. It's the phase diagram. The way I put it this way because this is more useful for my purposes. So this is the H, if you remember. This is the transverse magnetic field, and this is the A, the anisotropic parameter. Here we have a critical line. This is in the universality class of the Ising. This is the Ising line. So this is the transverse field Ising model. And then this one is the XX. So here, in this part, this XX chain is also critical. But the universality class of this guy is different from this one. OK, so what is this green region? So the green region is something, it comes from this relation. And you can show that actually in this green region, if you look to the group velocity with respect to k, you see two maximum group velocity. And with the two, I mean one is the global one, and the other one is a local group velocity. And then that makes actually the physics a bit, in different parts, a bit different, as I will discuss later. So this is what I already said about it. And then here, then usually you can think about the Fermi velocity in this critical region. This Fermi velocity is going to be 2a. And interestingly, in some regime, this Fermi velocity is not the maximum group velocity. And that will be also important later. Well, I mean that I had this VG, the group velocity formula, which came from the dispersion relation. So if you plot it with respect to k, with respect to the momentum, then you'll see that there are, there are some funny, smaller, or sometimes even bigger maximums. So let's study the Loschmidt echo for a simple case, and the simple case can be like you start from initial Hamiltonian, which is H0 and A0, and you go to the H and A. So you just change the parameters that you have. And then you can study that the Loschmidt echo will have something like this formula. This is something that people have, they really studied quite a lot, but it looks like there are some stuff that was missing in their studies, and that's what I'm going to talk a bit about it. So their conclusion is that the structure of revivals are independent of the initial states and follow the quasi-particle picture, with first revival related to the fastest quasi-particles. Then I will show later a bit of some figures in a way that you can actually picture the things. But this is the idea. And there is another work for local quenches, which says that for local quenches to the critical region, the Fermi velocity is going to be more important. So there is a region that actually the form of the revivals can be described by the Fermi velocity, which as I said, it's not always the maximum group velocity. Well, so of course, if you see something like this here in the local one, it should be already there also in the global one. But of course, people, they didn't really care much about maybe the critical region. So that's a part I will discuss a bit here. So the way that this is our version of doing things, but essentially it's the same thing as theirs. So what you can do to calculate the Loschmidt echo is just what you need to do is start. You have this H, which is a quadratic, then you just open this with a really old technique. People have been rediscovering this formula for forever. And then it is possible to open it like this, and this X, Y, and Z are going to be related to the A, B, minus B, and minus A. Here, this is pretty generic for every Hamiltonian is valid. In other words, every free fermion Hamiltonian. So it's independent of dimensions or the details of A and B. So at the very end, your calculation boils down to, for example, if you are interested to the initial state, which is you don't have any fermion, it boils down to just this determinant of T22. Later, I'll come back to more generic states. So, but this is just a warm-up. And then you can actually calculate this T22 exactly, and T1 to actually, you can calculate this T for the periodic XY chain analytically, and you get all these matrices. And some of the other matrices, they will be useful later for other quantities that I'm going to discuss. So that's the reason that I'm putting it here. So, but the real form is not that much important, but it's possible to do these things, and it's pretty standard. So then we have that equation. So you plug it in this formula of the Loschmidt echo, and then you end up to something like this. So this is valid for all the points of the phase diagram. And again, a bit of mathematics. Just I'm writing these things to just see that they are exact results. And then you can just start to analyze them numerically. Well, what you see that in numerically, this is A equal 1. If you remember, A equal 1 was the Ising line. So in the Ising line, everything is fine. It works. And based on, you can understand all these revivals that happening using this maximum group velocity. So these distances can be calculated using the maximum group velocity. Although that there is a bit of here, like in the theory community, we say it's a bit of like a pseudoscience in the sense that it's not always very obvious how you define the revival in your system. But somehow you can just cook it, by visually, for example. But cook in a sense that you look at the system. Sometimes the revivals, they look pretty small, but then you don't see them. But then you start to magnify, and then by magnifying it, there is a point that you start to see that there are some significant. Let's say, revivals in your system. That will be more significant when I start to talk about more generic initial states. But here it's quite impressive in the sense that you have, like here, the probability is like 0.05, which is something which is huge. huge in the sense that I started with the initial state, which everything was 0. So if you think in the sigma z basis or the fermion basis, you actually have how many of these configurations? Like in this case, it's like I think this is like for 80 sites. It's like 2 power 80 possibilities, and this guy is coming back to itself with this huge probability. The other example is the open, in the open case, based on the quasi-particle picture, actually these distances should get doubled, and they really get doubled. But this is not the major thing here. Then you can look to the h equal 1 case, which was the critical one, and then you realize that actually the phenomena that Stefan and Dubai observed for the critical cases is also valid here. So although there are some, in some cases you have a quasi-particle which is faster than the Fermi velocity, these revivals are associated with the Fermi velocity. So these are just some pictures that they confirm this observation. And then in the regime of that green region that I told you, which we have two group maximum group velocities, you can see something interesting in the revivals. There are some. It's difficult to say that sometimes you want to say chaotic, but I don't mean any chaotic in your sense. It's just not something that you can just explain it simply with the quasi-particle picture. So these first revivals or these revivals are nothing to do with that, with the group velocity of the quasi-particles that I was talking about. So this is a funny effect, but still not impressive much. Well, so let me conclude a bit what I said. So what happens is that in the white region, which I have just one maximum group velocity, everything can be described with this maximum group velocity. Then in the critical region, you need to look to the Fermi velocity. And then here, it looks like you don't see periodic nice revivals. Well, this picture will change later when I start to talk about more generic cases. So the initial states that I'm interested are this kind of initial states. So I have all the spins. You can think about either spins or think about the fermions. No? So in this case, you can think about not having any fermions, or here you have one fermion, nothing, one fermion, nothing, and then I think the definition should be quite simple, But I define them also in different ways. So here it's clear, here is 0, 1, and this is the way that I classify them, in the sense that X is, so you take a base of your system, like, for example, in this case, you have 4 spins here, and 1/2 of them are actually down, so you put it here 1/2. But the reason that I put 2 here is that these 2, both of them are 1/2, but here I have 1 spin down, and here I have 2 spin down. So in this way, you can generate a lot of crystal configurations, but they are not going to exhaust it, but exhaust all the possibilities. But that's not what I'm trying to do here. But these are already, you can produce a lot of different initial states like this. Well, you can also define some stuff by make them study the combination of them like this. This is not the part that I will discuss about it, but mostly I will talk about these things, but these are also interesting for their own sake. So so far I was talking about the full system. Now I just want to talk about a bit about some motivations that I had from a non-dynamical system. Here I want to talk about something which is you can just turn off if you are not interested to something which is not dynamic for 10 minutes. but I want to emphasize that here I'm going to talk about not something which is not dynamic. At the same time, it's not going to be for a full system, it's going to be for the subsystem. Everything can be done here also for a full system, but the subsystem has much more interesting things to say. So that's the reason that I will focus a bit on the subsystem here. But later, I'll come back to my initial states, and I'll talk about what happens with those initial states. So here I want to talk about something which we call formation probabilities. And the formation probability definition is here, since I'm talking about the dynamic, non-dynamical system. So I'm just talking about the ground state. So let's now go to the ground state of a spin change system. It doesn't need to be really spin change. It can be a spin system, whatever, you know. So whatever quantum system. Then you write it in a local basis. For example, if you think about this spin system, then if you take, for example, the sigma z, then here they are going to be all up, you know, all these possibilities that you might have. You might write it in a sigma x basis or other basis. But let's say that you choose your basis, and then you ask a very basic question. What's the probability of having a particular configuration here? So this is something that, you know, for a long time people have been studying, but mostly they were studying in an integrability community, but they were usually, I mean, the first things that you might say is that, look, you can choose like infinite different bases, and for different bases you will have different things. Is there anything interesting there? So that's, but I will try to show you that there are interesting things here, and that's the reason that I'm studying them. So the particular case of all the spins up is something that people have been calling it emptiness formation probability in the integrability community. So formation probability usually decays exponentially, which is expected. So you write it in you write your ground state in a local basis, and then you have exponential number of configurations. So if you look how the probability changes, I mean, with the subsystem size, it should decay exponentially, well, or even maybe faster, normally, if you don't have something which is exotic. So it's better to define a logarithm of this guy. Then of course, the first thing that you will be interested to study is the critical transfer field is in chain, and an interval with the length s. And people realize that this is going to change the logarithmic formation probability linearly, so which means that this guy is actually decaying exponentially, with but with the extra subleading term, which is the logarithmic. Well, whenever there is a logarithm, we are excited, and we want to know what is this logarithm, because we expect usually the coefficient to be some sort of a universal. And this has been answered by Jean-Marie Stéphane. He just considered here I'm just writing a periodic system, but it can be infinite. So his argument was like this. So if I just say that I want to have here all the spins up, I can think about this probability like the probability of freezing all these spins here, and then I can go to the Euclidean space and say that if everything is freezed here, then here this part is not going to have any contribution in the free energy. So what I need to do is just calculate the partition function of the full system without this slit here, without this just line, over the partition function of the full system. So that's the whole idea. So now, if the system that you have is at the critical point, and if this boundary condition that you have here is a conformal boundary condition, then you can calculate this, and then you realize that this coefficient is actually central charge. And that's the good thing, because the central charge in conformal field theory tells you about the universality class of your system. So we know that for the Ising chain, for example, this C is actually 1/2. And this with 1/2 and 1/8, we get that number that was calculated for the transverse field Ising chain exactly. Well, of course, you know, there are a lot of assumptions here. Recently, I'm getting more afraid whenever I want to use any field theory arguments for discrete systems, because there are a lot of if and if and if. And the if here is that the configuration that you choose here needs to induce a conformal boundary condition there if you want to have this result. Well, a priori, we don't know what configurations are going to be conformal boundary conditions. So that was the motivation for us to study, again, the XY chain and try to see, at least in the sigma z basis, what are the interesting conformal boundary conditions. In other words, those that they are going to lead to the same formula that I wrote for you. And so here, you know, I just put it again just because to tell you that now I'm talking about a subsystem. I'll come back later to the full system again. So these are the same configurations that I told you. Now you do the same. We have this Hamiltonian. So here to calculate these probabilities that I told you and check that which ones are going to be conformal and which ones are not going to be conformal, I need this matrix. I call it some sort of green matrix. I think some people, they call it green matrix. So you have these fermions here, and then out of them you produce this A and B, and then you look to the correlations of this guy. And this rho is going to be reduced density matrix. So how do we do it? So we use the fermionic coherent states. Fermionic coherent states, this is the definition. This is the technique that Peschel has been using for a long time to calculate entanglement entropy, but here I'm going to use it to calculate diagonal elements of the reduced density matrix. So the difference of what I'm talking here with the normal entanglement entropy is that in the entanglement entropy you diagonalize the reduced density matrix and then you look to the eigenvalues. But here what I'm talking about is are just the diagonal elements of the reduced density matrix themselves. So this is well, of course, naturally it's, the other one is kind of unique, but this one can have different behavior. So if you write this reduced density matrix in the coherent basis, which has this form, then what you can do is that if you put a C here, 0, that means that you are actually talking about a configuration which there you don't have any fermion. But if you want to put a fermion there, what you need to do is you need to Grassmann integrate that variable in that side. And then when you do it, you end up to a very simple equation. This is going to be the probability of whatever configurations that you have. So this is going to be the determinant of this matrix, which we know exactly, multiplied with the principal minor of the matrix F. And the matrix F, we know it. So the principal minors of the matrix F are going to tell you the probabilities for the different configurations of the fermions that you have. Well, so far so good, but normally the problem is that we can't calculate these things exactly. We can calculate this part, and this was already calculated by the Franchini-Abanov when I talked about emptiness formation probability, because this G matrix is actually a Topliss matrix, but then the F matrix that we have is doesn't have any interesting properties. So it's difficult to find any scaling limit results for here. But you can do very fine numerical things with this formula. And the reason that you can do good things is because you can really go to up to 5,000 size. So the results that you get, and you can actually work in the infinite limit. So it's something that when you can get out of it very good results, that you can trust. And the funny thing is that for all the configurations that I told you, we always have this formula, which for the Ising case is going to be 1/16. Sorry, this is actually C/8. I missed this. And for the XX chain, this is going to be like 1/8, because for the XX chain, the central is. But I just messed up here, I think. So the moral is that all the configurations that I told you, they are going to flow to some sort of a boundary conformity theory, and that formula, which I showed you for the conformity theories, is going to be valid. But there is a tricky issue here, and the tricky issue is that we know that in the CFT we have two conformal boundary conditions in the Ising CFT, fixed and free, and for the XX CFT, those that they are familiar with the Lottinger liquid, they know that we have Dirichlet and Neumann ones. And interestingly, you can actually realize that some of the configurations that I showed you, they are going to flow to free boundary conditions, and some of them, they are going to flow to fixed boundary conditions. So this is some sort of experimental work you study, and then they start to pop out. You know, for some reasons, some of them they go to the fixed, and some of them they go to the free, and it's usually not easy to predict which one is going to what. But at least for the configurations that I told you, we know the results. Well, I think this part I already talked about. Maybe there is a funny thing that I should mention here. And in this case of X exchange, since we have this U1 symmetry, the configuration with the all spins up is not going to be conformal, but the up, down, up, down, up, down is going to be conformal. And this is maybe also expected because of the U1 symmetry that I was talking. So, how all these things are connected to the Casimir energy? So the way that they are connected, first of all, let me tell you about what is the Casimir energy. So you put a couple of objects in a fluctuating medium, and then these two objects are going to either attract each other or repel each other. This is the famous Casimir things, but usually they call it the thermal Casimir effect. And this is an effect that the force can be calculated exactly in conformity theory. You don't need to care about the formulas. And if you think about the derivation of Stefan, you can see here that it is actually possible to think about the same thing for the formation probabilities that I said. Here you just need to think about, instead of the probability of one region, you can think about the probability of a particular configuration in two regions, and then you go to the Euclidean version, and then you see that you are going to have two slits here, or you can think like you put two needles in the fluctuating medium. And then these probabilities are, the probability formation for two regions is going to be related to the Casimir energy. So this was an observation. Then you can calculate the formation probabilities for these guys. The formulas are not important, and so these formulas are valid for any critical system in principle. So if you take any spin chain at the critical point, these formulas are going to be valid. But the interesting thing is that, well, the reason that I studied these things is that the one interval was giving us the central charge, and I was interested to something more. Something more means that you want to know what are the scaling exponents that you have in your universality class. So that's the motivation. So you want to have the central charge and the critical exponents. And the two regions that if you study the two regions, then you get this kind of information. So this is a bit of numerical things for the XY chain, and that actually works pretty well for the XX chain and Ising chain. Here I'm taking up, down, and here I'm taking up, down, or down. Well, so what I wanted to say you that this quantity of just looking in the local basis sounds stupid, but it gives you really the universality class of your system. It gives you the central charge. It also gives you the critical exponent of your system. And so how much? Well, I didn't even. So I just go. So let me tell you a bit about the different initial states. So With the same technique that I told you, you can calculate the Loschmidt echo for different initial states. So you put this the coherent fermionic bases, and then you do the same kind of calculations, and so you can calculate, for example, exactly for the configuration of 0, 1, the Loschmidt echo, with the same technique of the coherent bases. And then what is interesting is that in this case, you realize that the revivals are actually related to not the maximum group velocity, but the group velocity at pi over 2. And this is valid for all the full phase diagram of the system, independent of being critical or green or white. And for the other configurations, you see that if you take 1p over 1, then you can see that this is a bit of playing with the numeric. And then you realize that you can change the initial state, and then you see that you are making important particular quasi-particles with a particular group velocity. And this one-point function, you can do the same thing with the one-point function, and that also confirms the same behavior, which is not surprising because Loschmidt echo is actually the full state. Here I'm talking about just one correlation function, one-point function. And you can do the same thing with the correlation functions. And here you also see that actually the light cone velocity that appears is going to be dependent on the initial state. This is something that, well, as far as I know, it wasn't expected by people that I talked with them so far. For this states that I told you, it's not the first time that it was observed in a critical change. It was already observed by these guys for the XXZ change, but they were starting with the initial state, which was not a pure state. It was a Gibbs state, and then they were discussing that it's going to be related to the energy density of the post-quench Hamiltonian. But in our case, this argument is not valid. I think what is important is here is that for different states usually you need to do independently different calculations. So I'll skip this the evolution of the Shannon. So I told you a bit about the initial state effect on the Loschmidt echo and the XY chain, pretty rapid, and the revivals of the filling operators. I just showed you that how the initial states can actually change the structure of the revivals and the light cone group velocity. And some interesting quantities like formation probabilities and Shannon information. Thanks for your attention.
Thank you very much.